This is the first section, Chapter 2, Section 2.1, Linear Functions and Models. These are the topics we'll be covering during this presentation. So the first question we have to ask ourselves is why mathematical models? Well, mathematical models are used pretty much in every field today, from sports to business to science, technology, astronomy, religion. And regardless of the field, all models have two of the following properties. First, the present property is what I like to call it. A model is able to explain present phenomena. In other words, we can create a model to explain or show the buying habits of certain consumers. And pretty much none of the data that we're going to see is going to contradict our model. Our model will be able to explain pretty much all the data that we are able to view. It also has a future property. In other words, the model is able to make predictions about data or results. So based on the current data, we can build a model that will help us predict future phenomena. It'll also be able to help us predict past data. So if, say, we know some information currently, but we want to kind of predict where things were before, then a lot of times we can use the model that we have to predict what's in the past as well. Now there's two types of models we're going to look at. The first one's an exact model. An exact model is basically where all our data points match the function that we're given for the model. Here's an example of a linear function, f of x equals 4x minus 5. The data points we're given are negative 2, negative 13, negative 1, negative 9, 0, negative 5, 1, negative 1, and 2, 3. This is our domain, all our inputs. And if we input each one of these data points into our model, lo and behold, we wind up with the exact match coming out on the other end that pairs up with this data point. That's an exact model. This is not very common. Most of the times we have what's called an approximate model. An approximate model basically says, our data doesn't behave perfectly, but here's a great approximation. This is a very good close estimate of what we're observing. This is how an approximate model may occur. This is the function f of x equals 2x plus 3.5. Here are the data points that we observe: negative 2, negative 1, negative 1, 1.5, 0, 3.5, 1, 5, and 2, 6.5. If we plug each of these data points in, notice not all of them are exact matches. Only the second one and the third one are. The rest of them are approximate matches. The y value for the data was negative 1. The actual y value of the function was negative 0.5. Not exact, but pretty close. Same down here. This y value was 5 for the data, and the model was 5.5. Again, approximate matches. This is more common. What we're going to see is that our models will give us close representations of what our data is actually showing. So we're going to talk about many models in this course. The first model is going to be the model of what's called the linear function. Now, representations of linear functions, we know that we can represent functions in many ways. We're going to look at symbolically using equations. We're going to look at graphs, and we're going to look at tables. Here is the function f of x equals 1 half x plus 3. Here is its graph. We need to be able to tie this function to this graph. So let's look at the properties of the graph. We look at this graph. As x increases by 2 units, we notice that y increases by 1 unit. So if I come across here, I go over 2 units and up 1 unit, I hit the graph again. Again, if I start here, go over 2 units, up 1 unit, I hit the graph. This constantly repeats itself. So we do know that over 2 from left to right is a delta x of 2. Up 1 is a delta y of 1. So we know our slope is delta y over delta x. So this tells me m is 1 half. We also recognize from this graph that this function hits the x-axis at the point 0, 3. By definition, this is known as our y-intercept. So from this graph, we can identify both the slope and the y-intercept. And notice our function is f of x equals 1 half x plus 3. The 1 half is the slope, which we identify in the graph. And the 3 is the y-intercept, the y-coordinate of the y-intercept, which we can also identify from our graph. We could also use functions with tabular representation. We are able to identify, the graphs are a little bit easier to see. We can look at a graph and say that's a straight line. Tables are a little bit trickier, but if we look at a table, notice each of these x values differ by 2. In other words, the distance from negative 2 to 0 is 2. Distance from 0 to 2 is 2. The distance from 2 to 4 is 2 as well. So that's my delta x here. It's constant. My delta y, notice they were nice enough. If the delta x's are constant, which makes your job a little easier, we just have to check the delta y's. In this case, the delta y's, they're constant as well. Change from 2 to 3 is 1, from 3 to 4 is 1, and from 4 to 5 is 1. So again, if I were to look at delta y over delta x, these are each constant and their ratio. Delta y over delta x is constant. Delta y is 1, delta x is 2, their ratio is 1/2. So again, that's where my slope comes from. And again, if I look at my table, by definition, your y-intercept is always where the x value is 0. So here is 0, 3. This is the 3 on my function. So let's look at an example of getting an equation from a graph. If I have a graph here and I want to find the equation of this line, we know it's a line just by kind of eyeballing it. But the easiest way to do it is to kind of mark 2 points that are already on the grid. Notice the grid is put in this graph for us. So I'm going to mark the point 0,4 and the point 3, 2. Now the point 0,4 by definition, since the x-coordinate is 0, that means this is the y-intercept. And I'm going to move from this leftmost point to the rightmost point. The reason I do that is moving left to right. If you go left to right, your delta x is always positive. That way all you have to do is worry about going up and down. Well, I know delta x is 3 because I'm going from the y-axis all the way over to this point, which is 3 away. And my delta x is 3. My delta y is negative because I'm going down 2 units. I'm going 4 down to 2. So therefore our delta y is negative 2. Our delta x is 3. Other way we can do is just count. We count down 2 and over 3. Remember, your slope is rise over run. So therefore, from this graph alone, I can look at it and say this function is f of x is negative 2/3 x plus 4. This is my slope. That's my y-intercept. I can also do this with a table. If I look at a table, we don't have to necessarily plot these points, but we can sit there and look at it again. We notice the delta x is consistent. It's 2 all the way down. If we look at the delta y, we're going 4 all the way down. Sorry about that. I have some wrong data values in here. That should be a 9. I apologize. So we have 9, 5, 1, and 3. The delta y is negative 4 all the way down. So again, your slope is change in y over change in x. So negative 4 over 2 is negative 2. So my function is f of x is negative 2x plus 5. And again, we can get all of this from our data table. Alright, what to look for when modeling with linear functions? We do know one couple of things. Number one, the linear function has a constant rate of change. In other words, the slope is constant. So if I pick any 2 points and go over and up or down, that's going to give me my slope, whatever that slope is. If I repeat it, if I go over the same delta x and down the same delta y, I'm always going to hit another point on this line. And I can pick any starting point and that will hold true. Now, when I'm talking about linear modeling, whenever I sit there and pick my y-intercept, I usually sometimes consider this the initial value or the starting point of the function. This makes sense especially if we're measuring x in terms of time, because usually we start at time 0 and count up. Now, when I'm trying to model a linear function or phenomenon, I'm looking at f of x equals mx plus b. M is our slope, b is our y-intercept. But a lot of times I want to think of it in these terms. F of x is the constant rate of change, or slope times x, plus the initial amount. Let's look at an example of this. We say we have a 30-gallon bathtub that's full of water, and the drain is pulled on the tub and it begins to empty at a constant rate of 5 gallons per minute. Write a function that models the number of gallons in the tub after x minutes. Well, we can draw a graph, sketch it out if we want to. However, we do know right away, since the water drains at a constant rate automatically implies a linear function. So I know that f of x equals the constant rate of change times x plus the initial value. If I were to actually write an equation for this, our constant rate of change is negative 5 gallons per minute, because we're told that it drains. In other words, I'm losing water at 5 gallons per minute. The initial value, we started out with 30 gallons. So if we remove the units, the gallons per minute and the gallons, we wind up with f of x equals negative 5x plus 30. We now have our model. We can now predict how much water will be in the tub after, say, 2 minutes or 4 minutes. We can sit there and make predictions in our model. However, we need to recognize also the domain of this model is limited. It only goes from 0 to 6 minutes because it doesn't make sense to continue to lose water out of an already empty bathtub. Nor does it make sense to go back in time beyond where the tub is full. Our last topic is what's called a piecewise defined function. Sometimes a model requires more than one function to describe its various parts. An example would be that of a taxi. When you get in a taxi cab, a lot of times they will charge you one method for the first mile or the first tenth of a mile or quarter mile, and then after that they charge you in a different method. In this case, we have to use a function that's defined by its different pieces, hence the name piecewise defined function. This is typically the way we write a piecewise defined function. Let me show you the graph first. Notice that this graph follows a very distinct pattern all the way up until I get to this x value of 2, and then it changes and follows another pattern. This is what we mean by piecewise defined. For one piece of the function, it's defined one way, and then there's a break, a distinct break, and then it's defined another way. Notice this break occurs at x equals 2. So notice that when I write this function, I write it in two distinct parts because there's two distinct pieces of the function, and then I define one piece up until x equals 2. It says x is less than 2. And then the other piece for x greater than or equal to 2. Notice that is my breaking point for where this function changes from being defined one way to the next. Let's see how we evaluate this. Say I want to sit there and plug into this function. I want to evaluate the function for f of 0, f of 2, and f of 4. We're going to use this criteria over here to the right when it says where it's defined. This top piece is defined for x less than 2, and this bottom piece is defined for x greater than or equal to 2. Well, in this case, when I look at f of 0, 0 is clearly less than 2. So what's going to happen is when I plug in f of 0, I'm going to be plugging 0 into this top piece, the 2x piece. So f of 0 is 2 times 0, which is 0. The next one, I'm going to be plugging in 2 into this bottom piece because 2 is my x value, and 2 is not less than itself, but 2 is greater than or equal to 2. So I'm going to plug it into the bottom piece. So I'm going to get 1 half, negative 1 half, times 2 plus 5, which is just 4. Similarly, when I plug in 4, I can't plug in the top piece because the top piece is defined for x less than 2, and clearly 4 is not less than 2. So I plug it into the bottom piece, and we get negative 1 half times 4 plus 5, which is 3. Be careful when you are actually evaluating these. This is easy to get confused, but you should have no problem as you get practice on it.